Hi, I'm Amrish Verma of Cadence Design Systems. Welcome to Sigrity Tech Tips. Today we bring you another installment of how to build and verify your multi-gigabit serial link to meet industry compliance standards. Our video today will show you how to build an IBIS AMI model without having to become a programmer. Since IBIS AMI models describe how the signal is equalized, they are a critical part of the serial link channel design when data transfer speeds exceed 5 gigabits per second. However, depending on where you are in the design cycle, you may not have an IBIS AMI model that allows you to simulate your transceiver. For instance, you may be early in the design cycle and trying to choose between industry standards such as PCI Express Gen 3 versus Gen 4. Or you may be late in the design cycle and you find out your chosen SerDes vendor cannot provide a usable IBIS AMI model for their device. In either case, Sigrity can help you create an IBIS AMI model that will allow you to move forward in your design process. Being empowered to create your own IBIS AMI model lets you customize your serial link design methodology and accelerate your time to sign off. The wizard-based process lets you select equalization algorithms from the Cadence library of equalization routines, parameterize those algorithms, and compile and link them together, creating an IBIS AMI model that will behave just as you expect. With the IBIS AMI model problem resolved, you will have plenty of time to focus on the challenging 3D aspects of serial link channel design, such as via transitions, curve traces, and entering and exiting dense pin fields on large devices that can make or break your channel design. With a complete serial link analysis solution in place, you will be able to pass industry compliance tests the first time, your product will get to market on time, your boss will look good, and you just might get a raise. In today's video, you will see us utilize the Allegro Sigrity SI base and system serial link analysis option. To learn more about these products, visit us at www.cadence.com. Now I will turn it over to my colleague Ken Willis.
Thanks, Ambrish. The test case we're going to use here runs a serial link from the transmitter through a package, card, connector, down a backplane, and then through another connector, card, package, and into the receiver. So the first thing we'll do is run a baseline simulation with no equalization. As we'd expect at this data rate, with no equalization, the eye is fully closed. So clearly we're going to need to add some equalization in order to open it up. With the AMI Builder functionality integrated into System SI, it's easy to create your own AMI models to your own specifications. They can be quickly created for either the transmitter or the receiver. In this case, we're going to focus on creating an AMI model for our receiver. The AMI Builder wizard will walk you through the steps in creating this AMI model. First thing to do is to give it a name. There are 3 submodules to the RX AMI Builder wizard that we're going to walk through. The first of these is AGC, or Automatic Gain Control. AGC essentially amplifies the swing of the signal to give some differentiation between the logic 1 and the logic 0 state. Through the wizard, you can model the AGC as a simple gain amplifier or as a time domain step, pulse, or impulse response file. These are just simple text files, and examples are provided with the wizard. If you hit the plot button, you can even look at a display of the waveform. For our case, we're going to model the AGC as a simple gain amp and allow it to adapt throughout the simulation. The target adaptation voltage is set for 100 millivolts. This means that the algorithm will attempt to make the median of the voltage distribution at plus or minus 100 millivolts. The next module in the RX AMI Builder wizard is for continuous time equalization, or CTE. CTE essentially complements AGC functionality. Where the AGC functionality tries to spread the 2 voltage distributions from 0 and 1 apart, the CTE attempts to sharpen up those distributions. Again, there's a couple of different modeling options here. The first is a built-in 2-pole functionality where the cutoff and the roll-off frequency can be automatically calculated based on the data rate. This is very similar to that defined in the PCI Express specification. The CTE filter can also be described with a variety of simple text file formats. These can be in time domain, frequency domain, pole 0, or rational function formats. For our CTE, we'll use a time domain narrow pulse response file. Again, this is just a simple text file which can be easily plotted right from the wizard. There's just the one pulse response in this particular CTE file, so we're going to say no to adaptation. The next module is for Decision Feedback Equalization, or DFE. DFE feeds back previous bit decisions to help cancel post-cursor ISI, or inter-symbol interference. One of the key parameters to define for a DFE is the number of taps, which essentially define how many unit intervals out it looks to make corrections. Another key parameter is whether the DFE is digital or analog. A digital DFE will make an adaptation every X number of bits that it samples. An analog DFE will adapt continuously on every bit. The clock and data recovery, or CDR function, will automatically be integrated into the DFE module. And that's it. After providing a little bit of data and answering some questions through the AMI Builder wizard, an AMI model is automatically compiled for you in the background. When it's finished, it automatically appears in the System SI canvas attached to the receiver of interest, and it's ready to simulate. Let's take a quick look at the model. If you double click on it, you can see all the parameters associated with the model. Here's the AGC section. Here's our CTE section, and you can see that our narrow pulse response file is defined in there. And then on to the DFE, where you can see our 5-tap digital DFE defined. The next step is to try it out and see how it works. Since we're right in the System SI environment, all we need to do is hit the Simulate button, give our simulation a name if we want to, and off we go. During the channel simulation, you'll get real-time plots of the eye as well as of the DFE coefficients, so you can see how they're adapting. The 5-tap coefficients here have settled out pretty nicely. With the channel simulation completed, you can see with our new AMI model at the receiver that we've actually opened up the eye, whereas initially it was completely closed. So our AMI model appears to be working as expected.
Thank you for watching another edition of Sigrity Tech Tips. For information on products used in today's video, click on the links below or contact your local Cadence sales representative or Cadence channel partner.